Hi everybody, today we have the first lecture in the Drillbench fundamental course. Drillbench dynamic drilling simulation software for design and evaluation of all drilling operations. The lecture 1 is an introduction of the theory about the drill bench. What is a drill bench? It is a dynamic drilling simulation software for design and evaluation of all drilling operations. It is a result of more than 25 years of drilling research and has unique features in dynamic simulation of the wellbore flow process. Drillbench is a combination of several individual applications. It has 5 applications inside this Drillbench, focusing on different challenges encountered in a drilling operations. Drillbench software provides a user-friendly tool that targets all drilling engineers involved in challenge well. What is a drill bench again? The drill bench is built around the well control workflow covering first one, pressure control. This is the covering, well control and blowout control. This allows you to couple your well planning to operation workflow and provide essential input to deliver safe and efficient well construction. We have here the primary well control, secondary well control, and tertiary well control. Primary well control consists of steady state hydraulic and dynamic hydraulic. The secondary well control, dynamic well control, and underbalancing drilling. Tertiary well control, blowout control, and we have here opened the symbol folder for some cases about the drilling operations in some demos wells, oil wells. Drillbench benefits. Drillbench as application or simulation software, it is consist of the, as I said, first primary well control, second secondary well control, and third the tertiary well control, as I explained last. The primary well control, hydraulic and temperature simulation to validate that all planning operation can be performed, Drillbench dynamic hydraulics. Secondary well control, evaluate kick tolerance and the best procedure for handling kick in this end, Drillbench dynamic well control. Tertiary well control, evaluate worst case discharge and the requirements for a dynamic kill operations in a blowing well, Drillbench control, Drillbench blowout control. Drillbench 3 models that cover the entire well control scope. The first one, Drillbench dynamic hydraulics, this the dynamic hydraulic, and Drillbench dynamic well control, and Drillbench blowout control. We have the 3 models that cover the entire well control scope. The first one, Drillbench dynamic hydraulics, enables the user to simulate planned operations and verify that the planned scope can be performed without exceeding the available pressure window. Drillbench dynamic well control focuses on how a potential well control incident based can be handled to minimize risk and loss of time. Drillbench blowout control focusing on tertiary well control. It will enable the user to evaluate worst case discharge rates and validate that the blowing well can be killed and controlled efficiently. Primary well control, steady state hydraulics and dynamic hydraulics. This is the first primary well control from the Drillbench simulation. Are both part of the primary well control feature in Drillbench, steady state hydraulic and dynamic hydraulic. The first one, primary well control, steady state hydraulics. Steady state is one of the applications in Drillbench. The program includes the flow modeling, laboratory and full-scale experiments and simulation and simulator development. The simulator uses advanced mathematical models in order to produce realistic simulations. A great number of special and complex well conditions can be handled. Steady-state hydraulic is a result of extensive research and development within hydraulics and well control performed in Schlumberger and SPT group, and it is focused on drilling hydraulic and modeling of the well bore pressure and the temperature during all phases of the drilling operations. Number 2, primary well control dynamic hydraulic. Drillbench dynamic hydraulic is an advanced hydraulic and temperature simulator and provide valuable insight on how the drilling operation is impacting the well bore pressure and available margins. An accurate dynamic hydraulic model, including temperature transients, is used for calculating well bore pressure for all operation drilling. How to calculate the well bore pressure for all drilling operations. Computations of pressure, equivalent viscosity, velocity, and equivalent circulating density during drilling are performed in the hydraulic modes. Secondary well control, dynamic hydraulic, and underbalancing drilling. This is the secondary well control application. We have two applications, dynamic well control and the second one, underbalancing drilling. The secondary well control, dynamic well control. Advanced well control engineering for planning, operations, training, and decision making support how to make the right decision for your operation, your drilling operation. Drillbench dynamic well control provide realistic simulations of kick tolerance, promotes safer operations. The program includes the results of activities like flow modeling, laboratory and full-scale experiment, and simulator development. The secondary well control underbalancing drilling. Drillbench underbalancing drilling is the fourth application in Drillbench. It is the impact of operational change on well bore. Definition of the underbalancing drilling. We have two definitions, the same. Number 1, it is the drilling process in which the circulating fluid bottom hole hydrostatic pressure is maintained below the formation pressure, the formation following pressure. Also, another definition, it is the operations when the hydrostatic pressure of a drilling fluid should be naturally less than the formation pressure being drilled. The territory well control, blowout control is the territory well control feature in Drillbench. Drillbench blowout control, powered by the Olga multi-phase flow simulator, enable drilling teams to perform dynamic analysis of possible blowout rates, dynamic kill rates in different scenarios through the drill string or relief wells, including required pumping volumes and duration and pressure loads. This is the blowout control. Drillbench overview as introduction about the window of the Drillbench. We have the main window of the Drillbench, and when we open the Drillbench, we can see all the applications from the first one, steady state hydraulic, dynamic hydraulic, and dynamic well control, underbalancing, and blowout. You can see what the windows of these applications consist of. Steady state, for example, if we open the steady state now from the Drillbench, we can see this window, the first window for the input, basic input, what it consists of. Summary, description, survey about the well parameters or well data, inputting all of these parameters. Formation, bore pressure and fracture pressure, well bore geometry, string, mud, and other parameters. Now we will opening the Drillbench to see what it consists of. Now we will open the bench from the my laptop. We have the Drillbench version of 2022 version 2.1. Double click. It is the main window of the Drillbench. And if we want to go to the dynamic hydraulic or to the steady state hydraulic to overview the Drillbench software. For example, if I see the steady state hydraulics, this is the primary well control for the Drillbench. We have the navigation bar basic input. We have this 9 parameters: survey, summary, decision about the well, survey, lead divisions. It is the division survey. If the well vertical, we don't have here any data. If we have the directional or horizontal well, we will input the measure depth, inclination, and azimuth angle of the direction to reach the target. And formation, we can input all formation, top and bottom formation for every layers here. And the Drillbench only we can make 15 formations or 15 layers. Bore pressure and temperature. Bore pressure, the tables, and fracture pressure, and here the pressure gradient will be see here. Wellbore geometry, about the wellbore geometry, casing liner, riser, and hanger depth, setting depth for the casing, production casing and or conductor, surface casing, intermediate casing, production casing or liner. And drill string, average sand length for every string, and components for the drill string, drill pipes, drill colors, and here we can bit data inside in this one. And we have the library here for select the bit with the size, bit size. For example, 8.5 BDC or BDC hydraulic, as you like. You can select and add. Total flow rate and nozzle diameter for the drill bit. Also, we have another parameter for the mud and cementing here. Drilling fluid, we can see the default or fluid name. We can also go to the library and take any oil based mud example or oil based mud example 2, 3, seawater if we drilling in salt formation, or spacer or water based mud example number 1, example number 2, with the specific gravity for all drilling fluid. And select any one and click OK to know about the shear stress and shear stress here and there for the drilling fluid. And we have the BVT model density calibration or measure as you BVT properties for the drilling fluid or mud. We have the temperature inside the well and pressure bar, density for the drilling fluid, density with pressure, and fluid density with temperature. Also, we have the edit fan table for the fan. It is the pressure bar, temperature and pressure bar. We have rate per minute in 600 or 300, rate per minute or 200, as we have in the field or in the laboratory if you like. Also, we have the plastic viscosity, yield point, low fan. We can input plastic viscosity, yield point, fan reading for the mud or drilling fluid. Also, we have the temperature gradient inside the wellbore. We have the dynamic model introduced from geometrical gradient, or dynamic model introduced from the table if you have the table, or static table, and we can input the mud temperature in drill string and mud temperature in annulus. And we have the constant mud injection temperature, also constant temperature difference if you have the difference between the temperature, surface temperature model if we have also. This all of the basic input. And we have the expert input, model parameters, number of grade cells in flow direction. We have efficiency, measure depth and efficiency factor. We have surface pipeline, if you have the surface pipeline for the well, and rich and choke. Also we have the simulation at the end, hydraulics. We have the equivalent density, pressure, temperature. We can see here, but we don't have now the data inputting for this well. If I open the steady state, for example, for the well, don't save. For the well, I have some cases here in my lecture number 1. For example, if I English course, we have the demo steady state hydraulic water based mud drilling fluid as the drilling fluid. Open this case or this well, we can see here, for example, as this summary about the description for this Hakim field in Libya Republic, Hakim directional well. It is the directional well. But before I know this well and this company, Schlumberger, you should first select the company, drilling company, immediate unit setting. If you have the metric urban or field unit, it is the foot by foot and metric by meter. If I have by field, you can select the unit definition, click OK. You can see all the parameters or the by foot. And if I select European metric, if the company use the metric units for the depth, or we can see here riser length 109 meters, casing show 4,400, and other. This is of the description or summary about the well, Hakim directional well number 1, and we have the drill string, geology, drilling fluid, water based mud, specific gravity, water based, and oil water ratio. If you have description, we can see, for example, which is the drilling company. For example, if I SLB, Schlumberger, or another neighbors drilling company, field, Hakim field, project development, the Hakim field project, rig company, the neighbors drilling company, drilling rig, well, Hakim directional well 1, section drilling department, creator engineer Labib Hugari. You can see here Labib Hugari, who is the creator for this well in Drillbench. And you can add here some description about the well. It is the directional well, development, about anything about the well. For example, location, surface location, and target location, because we have the directional drilling as a summary or as a description about this well. Survey. The survey, we have this as horizontal displacement and the directional well for the profile or well trajectory for this well. We can see the measure depth, inclination, azimuth, and the drill bench. It is calculated the vertical depth north-east. He is calculated by the theoretical function. And horizontal displacement, it is the horizontal displacement from the vertical axis. How is this distance from the vertical axis? And the target here, we can see also in 3D dimension for this profile or well profile. It is the vertical section, or right same to the vertical. From here we have the inclination angle to go to the straight to the tangent section, and here build up section to build up the inclination angle, and here we have the constant inclination angle, and at the end we should have in this profile the drop angle to get to the target. Formation, it has the formation 1, 2, 3, 4. For this we can write the name of the formation if we have the lithology columns for the area, and top and bottom for this formation or layers, and thermal gradient for every layer of formations. Also we have the bore pressure and fracture pressure. It is we will input the data, we can input the data for the real drilling well from the first one. In the lecture 2 I will explain how to input the data for every parameters from this 9 parameters. And we can, if you have this is inputting data is already, you can from schematic you can see the well geometry or well profile here. Like this. This is the casing and drill pipes or drill string inside the well, and conductor casing, surface casing and cementing, intermediate casing, production casing and production liner at the end. And it is the bottom true vertical depth or measure depth for the well. As we see here, the sitting depth 4,400 and the hanger depth 401, and we have the string size and bit size for this section. Also we have the mud properties, the drilling fluid water based mud to specific gravity 209 specific gravity, the base oil density 0.56 specific gravity, water density 2.06, and the solid density 4.2, density of the drilling fluid 2.09 specific gravity, and other oils. Temperature inside the well, you can see the temperature inside the well from the top to the bottom, and it is at the bottom measured of 0, we have the temperature 27 Celsius, and at the bottom of the well, at the end of the well, it is 153 Celsius, and this the temperature and pressure inside the well. We have the 330 window is the survey or deviation survey for the well. If the vertical will only the vertical. If you have the direction horizontal, we will see the profile or geometry for trajectory for this well. The input data for survey are measure depth, inclination angle and azimuth angle. The simulator calculate the true vertical depth. The Drillbench simulator will calculate the true vertical depth by using the minimum curvature algorithm. The inclination angle is given as deviation from the vertical axis, which means that an angle of 19 degrees indicates the horizontal, and we have the size from the surface location for the horizontal view. We have the north 0 degrees and south and east and west. If we have the directional or horizontal well, we should know where is our target or azimuth direction to drill. For example, if we have the target in this side, we will know that our direction it is 45 degrees from north. If we have the direct for the well in this side, that means it is the 90 degrees to the east. We will drill to the east, or everywhere we can know in which one of quadrant we will drill from the surface to the north or to the east or northeast. North 45 east, it is the direction, or in this quadrant, first or second or third or fourth, in which one we will drill to get our target. Azimuth is the direction angle measured from 0 to 359 degrees clockwise from the north to the position of the z-axis as seen in the horizontal plane here. The formation, it is the fourth about how to input your lithology or your formation layers inside the well with the top and bottom depth for every layer and geothermal gradient for every layer you can input inside or input this. And we have the maximum 50 layers can be added only inside the drill bench, not more than 15 layers. And we have in this formation also at the end of table the thermophysical properties. The formation section is only required the dynamic temperature model is used. If a measured temperature profile is selected, the formation section can be disregarded. Note that the last column in this formation, the thermophysical properties, in the lithology table contain on an option to edit the thermophysical properties for a different layers. Clicking the right hand, by clicking here in right hand side of the last columns, activity the cell for edit and a button appears in the cells. If you have the click in this one, where is the 3 points, by right click you can see the thermophysical properties editing, and you can have your customized density and thermal conductivity and specific heat capacity. Clicking the bottom open the window shown in figure 9, and you can see this figure 9. Bore pressure and the corresponding fracture pressure can be specified for various depths. This is an optional window and can be left empty. You can left this empty without any data. However, the given data will be used as a reference value in plots of equivalent circulating density and pressure. We have this the bore pressure and fracture pressure inside the drill bench application, and we have the bore pressure and fracture pressure and the plots for the bore pressure, the yellow and the blue, and the yellow it is the fracture pressure inside the well. And the wellbore geometry, we have the wellbore geometry section contains the specific of the actual hole. It is the actual hole inside the well. The wellbore is divided into two parts. First one riser, if applicable, and 2 casing and liner inside the well. You can see here we have the components, tabs, section length, inner diameter, outer diameter, distance from the bottom, and thermophysical properties and properties for every string inside the well. Drill pipes, heavyweight drill pipes, drill colors, and drill colors 8 with the size. Drill pipes, and the length, section length, we have 1053 and 2631 for the drill pipes, and heavyweight drill pipe 2058, and other drill colors 276.2. And the distance from the bottom, we have the total depth for the well 6,232 meters or feet from the, as we see here, 6,232 feet. Look here, the string components. We should have the same numbers for everything. From the description or summary, you can see the bed diameter 252 inch, and here the same number. For example, also we have the total depth for the well distance from the bottom 6,232, and this is the same depth, and also this is the same depth in the description. Or if you have any mistake for the total depth from the parameter to another parameter, it is will be wrong or a mistake for in your application or in your drill bench, and you can't not run the simulation for your well. Schematic, you can see a schematic of the string can be viewed from the menu, or from the menu view well schematic, or from the application schematic, as I did previews. And we have the mud. In the next figure, the specification mud or drilling fluid properties are illustrated, and we have the gel polymer or water based mud, and we can inside the mud also we can add our casing cementing if you need to do the cementing for your well from your input data tables. The mud rheology, we have the mud rheology from the laboratory gel polymer, or if you have any of this one as example, it is already, or you can add your mud or drilling fluid with your properties and rheology for your drilling fluid. Also we have the temperature inside the well. It is the measured depth and temperature Fahrenheit inside the well, measure depth and temperature in the top and in the bottom. For the well, temperature in the top 16.6 Fahrenheit, and in the bottom 200 Fahrenheit. Now I think we do the introduction about our application. You can continue with me in the next lecture number 2, input a new well data as a real data for any well you have, or I will give you a symbol for a real data from my PDF file to input the well data for real well in the next lecture number 2. Goodbye, and thank you for your attention. Goodbye.